demonstration will focus on the use of the non-manifold geometry strategy to create a FEM with the intent of having contiguous solid meshes across solid boundaries that are just touching or even slightly intersecting one another. This is analogous to using glue coincident mesh mating conditions, but this new method leverages technology from the NX CAD authoring tools to more robustly identify solid body boundaries in an assembly context. It then represents those boundaries as shared faces across solid bodies, exactly like mesh mating conditions. The result is a more robust process and simpler user experience with respect to creating contiguous meshes across solid bodies. The intent with this model is to generate solid meshes on all the components of this compressor assembly. It is comprised of 480 solid bodies. Some of the solid bodies are just touching one another, some are intersecting. Now we're going to go take a look at assembly clearances using our assembly clearance checks and clearance browser to start. I'm going to look at a pair of clearance sets. So first I'm going to look at the stage 1 stator. I'll make that active and then edit that clearance set to show you what we have in mind. So we have a ring type solid body that is holding our stator vanes in place, and then we have 38 stator vanes that are inserted into that ring with a pin. So I'll cancel this, and then if we review the results of our check, we see that we have a bunch of touching conditions. So I can just march through this list and everything is just touching. I can maybe grab one of these and study the interference. Go into wireframe mode, we can see pretty evidently that yes, there's two cylindrical faces. There's a cylindrical face from the pin on the stator vane, and then there's a cylindrical face from the ring. They are just touching one another, having the same diameter. So then that is one typical condition that you have with respect to assembly situations and mesh mating conditions. Another would be where you have interference between components. So that is evident in another clearance set, and I'm going to use the stage 3 rotor to take a look at that. So if I edit that clearance set, it will highlight a set of bodies, in particular 3 bodies along the shaft, and then a whole set of solid bodies representing blades. And so then I will cancel that, and now you see that we have a set of hard interferences. So this is an interference of these 2 solid bodies and 2 adjacent blades. And if I march through those again, we just see a bunch of the same behavior. So I can take a look at that one again. I'll study that interference, and then we can zoom in here. I'll set my filter to solid body, and then you can see highlighted in red some of the interference or intersecting between these bodies. I can mouse over the body and you can see how the intersection is occurring. So that this would result in a sliver condition, potentially with mesh mating conditions. I tried to do a Boolean, I would get a unite. This would be taken care of, but I would maybe potentially lose that boundary between those bodies. This is definitely going to be a sore spot for us with our traditional mesh mating condition methods, and it's one that we will be able to address with the non-manifold method. So I'm going to exit out of the clearance browser now, and then the next step will be to create a FEM using a simplified version of this assembly. So I just want to focus on those 2 geometric situations in this idealized part. Create a new FEM using one of my templates. It just contains mesh collectors and nothing really special with respect to that template. Dialog opens up. We'll see that we have 2 strategies from a geometry point of view to use. I'm running version 2506. So we have, for polygon geometry, we have the manifold strategy and non-manifold strategy. So this is the new method. I'm not going to show that on this step. I'm going to stick with the traditional manifold approach that's been in existence for many years. So I'll go ahead and say OK to this, and we will get 6 polygon bodies created. Next step would be to perhaps do an interference check to detect interference or clearance. I'm not going to do that, but this is also just a reminder that you can do those types of checks within the FEM as well. But I'm going to next go straight into mesh mating. All the bodies and faces and let mesh mating automatically create its pairs using the default search distance. So it's a very small search distance. I'll say OK to this. We get 16 mesh mating conditions as glue coincidence. So that's all good so far. I can mating conditions by themselves. So I'll say show only here, not delete, but show only. Say OK. And then just for clarity, I'm going to modify the color of those faces. So I'll say edit display. I'll change the color maybe to a, how's that, strong coral. That's good. And say OK here. And then if I just mouse over a given face, it should be one face selected there. So one object is selected there, one object is selected there, and then you can just start to display maybe these bodies. I'll start turning on these bodies that are shared. So I can see that only one of these two faces is selected. So this one body is going to be the stator vane. So I go ahead and select that. You can see that it's connected to this mesh mating condition face as expected. This would be the ring. Body is going to be the other stator vane. And then you say a display adjacent and select those faces and maybe do like 3 adjacencies. I'll say apply, and you see that those faces are indeed connected to the ring. And I'll just, for completeness, I will hide bodies and turn on, and you can see that mesh mating face on each side for the pins is on ring as well. So we have the stator vanes connected to this ring at our just touching surfaces of the pins and pinholes at the mesh mating conditions. So I'll show only those mesh mating conditions again. Focus on the area around the turbine blade. The turbine, not the turbine, the compressor, but the blade at stage 3 of the compressor. So here, again, in a similar fashion, I can highlight the bodies. So that first set that first body is indeed, a blade body, and the second one is the second blade, and that last body is going to be the disc associated with that stage. And then if I do, say, a display adjacent again of those faces, so I'll pick those guys, for example, these here, just say apply, and they're going to pull in the faces related to those turbine blades. Sorry, turbine, but compressor blades. So let me show those all entirely again, and maybe hide the disc. And then what do we have with respect to our interference condition? So we have nothing really. So nothing happened in terms of mesh mating because these surfaces aren't touching within one another. The interference was greater than that search distance. So nothing actually happened in this case for mesh mating conditions. So we don't have a connection between adjacent compressor blades at that location. So that's kind of a problem. That's really the connection that you want to have, the most important connection of the connections shown here. So we can maybe look at that from another perspective, and I'm going to do that next using the imprint command in our second idealized part. Our second idealized part, and what I'm going to do is use the imprint command to create imprints between adjacent faces on adjacent bodies, or faces that are just touching one another, and then hopefully this will make an improvement to our mesh mating conditions that we end up getting created from this geometry. So the imprint object is going to, for the case of these pins and the pinhole, it's going to imprint edges from the pinhole onto the pin and from the pin onto the pinhole. It's going to produce a coincident pair of faces, and then we will create a mesh mating condition from that paired face information when we create the FEM. So that's the general behavior and logic with respect to the imprint command. It's also good to use this command with respect to sheet bodies when you need to stitch sheet bodies up. In this case, it's going to do something here with respect to this interference. I didn't entirely expect it, but once I saw the result, it made sense to me, but it's not going to be a complete solution for us. So I'm going to go ahead and pick all of my solid bodies and say OK. And this content that's being generated by this CAD feature is going to be consumed during our FEM creation and dates that we take from our CAD to our FEM with respect to the geometry. So that's a really handy feature. It was added a couple releases ago to our idealized part and geometry operators within the pre-post application. So now that I have that, I can go create a new FEM. And new FEM, I will use the same template as before. I'm going to use the manifold method as well. So nothing new yet in terms of the methods. I OK here, and then you'll see mesh mating conditions created. So it happened really quickly, but now we get this creation of 15 glue coincident mesh mating conditions, and that's directly due to that imprint operation. So similar to previous, we can take a look at our mesh mating conditions. So we'll display those by themselves with the show only command. Okay, and then hide those. And then if I set this to polygon face, I should end up with two faces here. So I selected two faces there, and then this will be like 13 faces, I suppose. Yeah, 13 faces in the area of the compressor blades. I can change the colors again, so let me do that. I'll change the color of these faces to that strong coral, or one of these strong coral. That works for me. I would use display adjacent here on these faces, and 3 rows, so I picked these 2 faces. I should get faces from the stator vane and then that the ring connecting or holding the stator in place. So I do. That's good. And then cancel that, and then focus in on this region again. So set my rotate reference, say to there. Now I get an imprint in a mesh mating condition where those 2 blade solid bodies are intersecting one another. So this is maybe not necessarily a good thing. I've got a sliver condition created here where these faces are now shared between the 2 solid bodies. So I once again focus on the 2 solid bodies as the blades. It's going to be the first 2. So I'll hide this one, and then these 2. You can see these are shared faces across these 2 bodies, but interestingly enough, we don't have a shared face that it goes through the length of the, at the cut plane, so to speak, of these 2 blades. So yeah, it gave us a result. It gave us a result based on the geometry that we have, which is a bit, in error, and so that error is showing up in this situation. So we now have a connection here where we didn't have a connection before, but it's not the type of connection that we want. So let's go back to our first idealized part and then create another FEM from this geometry, but now we're going to use the non-manifold method. So I'm now back in the first idealized part, and you can see I don't have an imprint feature in this part history. So I'm going to go and create a new FEM without any of that imprint information. And this new FEM is going to use the non-manifold strategy to create my connections between my solid bodies. I have only a tolerance to consider, so this would be similar to the tolerance that we used or defined in the mesh mating condition search option. You can think of this as a tolerance that a Boolean operator would use inside of the part file. like if you're going to do a unite or a subtract. So we'll go ahead and say OK, and it's going to start consuming that geometry. From a parasolid point of view, it tries to identify the non-manifold boundaries, and when it's done, it creates a group of non-manifold faces. So here it says it has 7 faces that were created. I can do a show only on that. And another thing to note is I don't have any mesh mating conditions. The only indicator that I have is the non-manifold faces is these faces in the group. So I'll do a show only of that group. Next I will change the display of those, change the color. So edit properties or display and do that strong coral again. And then if I do display adjacent, say on the pins one more time, this works in the same manner as before. So I pick 2 faces to apply, and it gets the faces from the ring and then also from the stator vane. Okay, so that's good. And then if I do that again here for these 4 faces, and so those total of 4 faces, maybe I'll do it, adjacency at level of 2, and you can see that now my blade is connected to my disc through that surface, and through that surface, the one over here as well, and the one here. But we also have an additional connection between the blades that we didn't have in our first 2 examples. So let me cancel this and go back to a full display of my polygon geometry. And if I select that group, you can see now I have a non-manifold surface going between my 2 blade solid bodies. So that's going completely through. And if I display, say, just one of these blades by themselves, so I'll do a show only polygon body, and I'll pick this one and say OK. So now I've got a surface here at that intersection. So what did it do at that intersection? It does something interesting in that you have no sliver surfaces like we did in the second example here, but the sliver was consumed, or it was retained on this body. You can see this body has its full representation, and then the body on the right is kind of, it's been trimmed off in a subtract body kind of way, so that the intersection that was this little bit up here is actually retained on this body and removed from that one, and then we retain our boundary via that non-manifold surface. So it is a in a way it's a mesh mating condition, but it's a different way to produce the mesh mating condition. It's a more robust solution for mesh mating. Overall, it's producing the same results as mesh mating, and plus a bit more when you have these intersections. Now I want to generate solid meshes. So I'll go ahead and produce, say, the solid meshes on the blade, or I'm sorry, the stator vane here. I'll call this stator stage 1. Maybe give this a size of 2, and I think to avoid distorted elements on the very small leading and trailing edges, I'll bump up the curvature, and I'll just say OK here. A bit of time. So we get our meshes on those 2 blades, and then I'll do the same thing for the disc. Go ahead and pick that. This time I'll set this to 50%, maybe an element size of 4, and selector as, I'll call it, I don't have a ring, but I'll use the shaft. So say OK here. Mainly that's going to give me a different color for the mesh, using a different mesh collector. I'll do the same for my two blades in the rotor section, and this will be, I'll do 2 and 75 again. Do rotor stage 3. Okay, so that gives me those meshes. And then, so generate a mesh. The disc, say 4 millimeters and 50%. This disc. So go ahead and say OK. We have our mesh, and start seeing continuity across these boundaries. So we definitely have continuity across the blades, at that non-manifold boundary. And if I zoom in here, we can see continuity here. On the shoulder of at the point where we have the insertion of the blade into the disc. And then, I can also just say show only these faces, and then say show only again related elements. So related elements to those faces. Make sure I pick it as well, and I'll say polygon face, select all. So it found 2,500 elements. So I say OK here, and then perspective of the stator and the ring, I get two meshes. So this inner mesh is going to be that for the stator. So I should be able to just hide that and then show it, and you can see the ring mesh appearing. So it's connected. Same is true here. And then if I zoom in this area, we see the meshes for the disc as brown, and the meshes for the rotor stage 3 components as this color. So for example, I'll turn that one off and turn it again, and so you can see the connected elements to the adjacent blade on this one, and then you see the connected elements related to the adjacent disc surfaces. So everything is working really well from a contiguous mesh point of view with respect to these non-manifold faces in the context of our new strategy, that being the non-manifold strategy. And I didn't have to do any imprinting of surfaces. I didn't have to create mesh mating conditions. I just used this one option where I know all of my touching or intersection conditions I want to represent as a contiguous mesh, and that this method will provide that in a very efficient manner. At this point, we can conclude by doing a review of the complete compressor assembly. The FEM was created using the non-manifold strategy, and we can take a look at that by editing the FEM, and we can see that the non-manifold strategy was used in its definition. There are 480 solid bodies in the model and 7 solid regions. There's one region for the rotor, shown as the blue set of bodies. As the green set of bodies. And then the stator regions are shown as the blue set of bodies. There's 3 stator stages that are just single solid bodies, so we can ignore those, and those are included in this group called manifold bodies. So I'm going to hide that group, and then what's going to be left is 477 solid bodies, all connected in various ways through non-manifold faces. I can then select the non-manifold face group, and this highlights all of the connections created between adjacent bodies using the non-manifold strategy. So for example, I can zoom in and see all of the stators, the stator vanes connecting to that stator ring at those pin surfaces. I can see adjacent disc bodies as it goes from stage 1, 2, 3, 4, 5, and 6, connected at planar faces or concentric surfaces. And then we can also see in the blade disc regions how the blades are touching or intersecting with one another, or touching shoulders within the slots of the disc. And then next step would be to also highlight the elements related to these non-manifold surfaces. This group, non-manifold elements, can be added to the display. This group contains elements related to those non-manifold surfaces. And once that appears, I'll zoom in on various sets of these elements so we can see the stator vane pin faces, both on the ring and the stator vanes themselves, and the connection that they make, as we showed earlier. We can see some of those planar faces and concentric faces connected as we move from one stage to the next. And then we also see connections between, say, the discs and blades, and then the blades themselves in a given stage of the compressor. That concludes our demonstration of non-manifold strategy using Simcenter 3D.